Welcome, everyone. If you are tuning in right now, you are stepping into today's deep dive.
Glad to be here.
Yeah, and we are exploring a topic today that is quite literally all around you,
Everywhere.
covering everything from the food on your plate to the structural integrity of your own bones. Today, we are looking at the invisible chemical forces shaping our everyday lives, specifically the mechanics of acids, bases, and salts.
We're drawing from a really comprehensive stack of scientific research and texts today.
Art, I want you to consider a really familiar scenario. Imagine you're at a big family dinner.
Oh boy.
You have consumed way too much rich, heavily spiced food.
We've all been there.
Right. And you are hit with severe heartburn. Instinctively, people might try a lot of different home remedies for this.
Sure.
Some might grab lemon water. Others might swear by a shot of apple cider vinegar. And some will mix a spoonful of baking soda into a glass of water.
Right, and from a biochemical standpoint, the correct choice there is entirely dependent on understanding proton transfer.
Okay.
Because that indigestion is caused by an overproduction of gastric acid, specifically hydrochloric acid in your stomach.
Makes sense.
So lemon juice contains citric acid, and vinegar is just dilute acetic acid.
Yeah.
Consuming either of those is effectively adding more free protons to an already acidic environment.
Which sounds like a terrible idea.
It is. It's going to exacerbate the issue completely. Baking soda, however, is sodium bicarbonate, which acts as a base. It introduces molecules that actively accept those excess protons, neutralizing the acid and pulling your stomach's environment back toward a manageable equilibrium.
Okay. See this structural shift in your own home. A highly relatable example from our sources involves turmeric, which is a natural indicator.
Oh, the curry stain example.
Yes, if you spill yellow curry on a white shirt and try to scrub the stain with standard laundry soap, the stain doesn't just fade, it actively turns a deep reddish brown.
Because the soap is basic.
Right. And when it interacts with the turmeric, it alters the electron arrangement in the pigment molecules, changing how they absorb and reflect light.
It's so cool to see in real life.
And then if you rinse that shirt with plenty of water, washing the basic soap away, the molecular structure reverts, the stain turns yellow again.
It is a perfect demonstration of a reversible chemical reaction.
Yeah.
Beyond turmeric, the most famous natural indicator is litmus.
Litmus paper, sure.
Right. Litmus is actually a water-soluble mixture of different dyes extracted from lichen.
Like the stuff growing on rocks.
Exactly. Lichens belong to the Thallophyta division, which is essentially a group of primitive organisms that lack true roots, stems, or leaves. In a laboratory, that litmus is usually absorbed onto filter paper, and the active molecules in litmus react to the presence of hydrogen ions.
Okay.
In an acidic solution, the chemical structure shifts to reflect red light. So acids turn blue, litmus red.
And bases?
In a basic solution, it shifts to reflect blue light. Bases turn red, litmus blue.
And researchers have obviously developed far more precise synthetic indicators to do the same job.
Oh, definitely.
Phenolphthalein is a great example from the text.
A classic.
In an acidic environment, it remains completely colorless.
Huh.
But the moment the solution crosses over into a basic pH, it turns a brilliant, unmistakable pink.
Methyl orange is another really common synthetic. It sits at a reddish orange in highly acidic solutions and shifts to yellow as the environment becomes more basic.
So they just give a really clear visual cutoff.
Right. These synthetic indicators give us distinct, sharp visual thresholds to work with.
Well, here's where it gets really interesting. Because indicators don't just operate in the visual spectrum.
No, they don't.
We also have olfactory indicators, which are substances that change their scent profile depending on the chemical medium they are placed in.
The mechanics of olfactory indicators are brilliant.
Yeah.
Think about it. To perceive a smell, volatile organic molecules from a substance have to evaporate, travel through the air, and bind to receptors in your nose.
Right.
The research highlights an experiment using finely chopped onions or vanilla essence, just to demonstrate how acidity and alkalinity affect this volatility.
Right. The experiment involves exposing cloth strips permeated with onion odor to different solutions.
Yeah.
If you drop a dilute acid, like hydrochloric acid, onto the onion-scented cloth, the strong onion smell persists.
The acid doesn't touch it.
Exactly. The acidic environment doesn't interfere with the volatile compounds, But if you apply a dilute base, like sodium hydroxide, the onion scent completely vanishes.
And that disappearance happens because the basic sodium hydroxide actively reacts with the volatile organic compounds in the onion.
It changes them.
It chemically alters them, often turning them into non-volatile salts. Because these new compounds are no longer volatile, they don't evaporate.
Which means they don't travel through the air.
Exactly. And therefore, they never reach your olfactory receptors. The base essentially locks the scent molecules down.
That is wild.
And the exact same mechanism applies to vanilla extract or clove oil. Their characteristic odors are completely neutralized in a basic solution.
It is a great reminder that when we smell something, we are directly interacting with airborne chemistry.
If we connect this to the bigger picture, we have to look at how these substances behave beyond just changing colors and neutralizing odor.
Right, they do a lot more.
Acids and bases are defined by their reactivity. They are constantly seeking to donate or accept particles, which means when they interact with other materials, the results are incredibly dynamic.
The interaction between acids and metals is a perfect example of that reactivity.
Oh, the pop test.
Yes. When you mix solid zinc granules with dilute sulfuric acid, you trigger a single displacement reaction. The zinc metal is more reactive than the hydrogen in the acid.
Right.
So the zinc atoms actively give up electrons to the hydrogen ions, displacing them to form zinc sulfate, which is a salt, and releasing pure hydrogen gas in the process.
And that released hydrogen gas is diatomic, meaning it pairs up as H2, and it is famously flammable.
Which is why the classic laboratory demonstration involves routing that newly formed invisible hydrogen gas through a tube and into a soap solution.
I love this one.
The gas gets trapped inside floating soap bubbles. When you introduce a burning candle to those rising bubbles, the hydrogen rapidly reacts with oxygen in the air.
Boom.
Exactly. The resulting combustion creates a sharp, distinct popping sound, a miniature, localized explosion that perfectly proves the presence of hydrogen.
That aggressive reactivity isn't limited to pure metals, though. Acids also have a highly specific rapid reaction with metal carbonates and metal hydrogen carbonate.
It's like what?
Well, if you take baking soda, sodium hydrogen carbonate and mix it with hydrochloric acid, you are initiating a multi-step chemical breakdown.
Oh, this is the mechanism behind every baking soda volcano science project.
That's the one.
The acid and the carbonate react to form sodium chloride, which is a salt, and an intermediate compound called carbonic acid.
But carbonic acid is highly unstable.
Right. Almost the instant it forms, it decomposes rapidly into liquid water and carbon dioxide gas.
That rapid decomposition is what causes the vigorous fizzing and bubbling. All that carbon dioxide gas is violently escaping the solution.
And how do they prove it's carbon dioxide?
To verify that the escaping gas is indeed carbon dioxide, chemists use a standard lime water test. Lime water is a clear solution of calcium hydroxide.
Okay.
When you pass carbon dioxide gas through it, the two react to form calcium carbonate. Calcium carbonate is essentially microscopic chalk.
Oh, interesting.
It is virtually insoluble in water, so it precipitates out as a solid, instantly turning the clear liquid a milky, opaque white.
So we see that acids act as chemical instigators, tearing molecules apart to release hydrogen or carbon dioxide. But the dynamic changes completely when an acid directly encounters a base.
That encounter is what we call a neutralization reaction.
Right.
Despite the term, it isn't so much a cancellation as it is a specific atomic pairing.
Well, so?
When an acid and a base mix, the acid provides free protons or hydrogen ions, and the base provides hydroxide ions. These two ions naturally seek each other out and bond to form H2O. Pure water.
And the leftovers.
The remaining ions from the acid and the base bond together to form a salt.
Which goes right back to our initial heartburn remedy.
Exactly.
The excess hydrochloric acid in your stomach is providing too many hydrogen ions. By drinking a solution of baking soda, you are sending in a base to intercept those hydrogen ions.
They undergo that exact neutralization reaction,
Leaving behind harmless salt and water and restoring the stomach's natural equilibrium.
it is a highly efficient transfer of protons.
But stepping back, we have to look at what physically unites all these different acids. Whether we are talking about the sulfuric acid in a car battery, the hydrochloric acid in our stomachs, or the acetic acid in vinegar, they all share a fundamental behavioral trait.
The unifying factor comes down to what happens when these substances interact with water.
Okay.
A fascinating experiment from the sources to prove this involves electrical conductivity.
Right. The light bulb test.
If you dissolve glucose or pure alcohol in water and attempt to pass an electric current through the solution, the circuit remains open. A light bulb wired into the setup will not turn on.
Nothing happens.
Right. However, if you add a dilute acid into the water, the liquid suddenly conducts electricity and the bulb glows.
Because the acid is providing the charged vehicles needed to carry the electrical current.
Exactly. An electric current in a liquid requires the presence of free-moving ions. This experiment demonstrates that acids, when dissolved in water, actively dissociate.
They break apart.
They break apart to release positively charged hydrogen ions, or H+I. The generation of these free hydrogen ions in an aqueous solution is the defining characteristic of an acid.
And for bases.
Conversely, when bases dissolve in water, they dissociate to release negatively charged hydroxide ions, or OH.
The critical detail here is the role of the water itself. It isn't just a passive container for the reaction. It is the active trigger.
Yes, very much so.
Our sources highlight a specific test using completely dry hydrogen chloride gas. If you expose a piece of dry blue litmus paper to dry HCl gas, absolutely nothing happens. The paper remains blue.
The acidic properties are entirely dormant.
Exactly.
Yeah.
Because the hydrogen atom is covalently bonded to the chlorine atom.
Without an external force, it cannot just detach itself.
But the moment you introduce moisture by using a wet piece of litmus paper, the paper turns red instantly.
The water is key.
The water molecules physically interact with the HCl molecules, pulling the hydrogen ion away from the chlorine.
However, hydrogen ions do not exist in isolation in a solution. As soon as that H+ ion is freed, it immediately attaches itself to a water molecule, forming a hydronium ion, which is H3O plus decay. That hydration process is what activates the acidic behavior.
And that exact hydration process, the interaction between an acid and water, is the source of a critical safety protocol in chemistry.
A very serious one.
Mixing a concentrated acid like sulfuric or nitric acid into water is a highly exothermic process. The chemical bonds breaking and forming release a massive amount of thermal energy.
The thermodynamic reality of this reaction is why you must strictly follow the rule of always adding acid to water, slowly and with constant stirring.
Never add water to acid.
You must never add water to a concentrated acid.
Oh, what?
If you pour a small amount of water into a large volume of concentrated acid, the hydration energy is released so rapidly and in such a localized area that it instantly boils the water.
Wow.
The water vaporizes into steam, which expands explosively, throwing the highly corrosive concentrated acid completely out of the container.
That's terrible.
The sudden, intense thermal shock can also cause the glass beaker itself to shatter. Understanding the mechanics of hydration is quite literally a matter of laboratory survival.
So what does this all mean for how we measure and navigate these substances in daily life?
We use a scale.
Right. To quantify this invisible exchange of protons, chemists use the pH scale. The P in pH stands for Potenz, a German word meaning power, so pH represents the power of hydrogen.
It is a logarithmic scale measuring the concentration of hydrogen ions in a solution.
Ranging from 0 to 14.
Yes. The scale typically ranges from 0, representing an extreme concentration of hydrogen ions and thus high acidity, through exactly 7, which is chemically neutral, pure water, all the way to 14, representing a high concentration of hydroxide ions and extreme alkalinity.
And because it's logarithmic.
Because it is a logarithmic scale, a shift of just 1 pH unit means a 10-fold change in hydrogen ion concentration.
And that logarithmic power is deeply tied to biological survival. Human biology operates within a remarkably narrow window.
Extremely narrow.
The pH of our blood and internal fluids must remain tightly regulated between 7.35 and 7.45, essentially hovering right around that 7.0 to 7.8 range.
Yeah.
If our internal pH drifts even slightly outside that window, our enzymes denature, cellular processes fail, and we cannot survive.
Our reliance on that specific neutral window makes us highly vulnerable to environmental shifts. The research contrasts Earth's delicate balance with the extreme environment of Venus.
Venus is intense.
The atmosphere there consists of dense clouds of concentrated sulfuric acid. Life as we understand it, dependent on aqueous chemistry near a pH of 7, cannot exist there.
But even on Earth, we see issues.
True. Industrial pollution can lower the pH of rainwater below 5.6, creating acid rain that lowers the pH of rivers and lakes, devastating aquatic ecosystems that can't adapt to the sudden influx of hydrogen ions.
Yet, despite our need for a neutral internal environment overall, our bodies utilize localized extremes to function.
Like the stomach.
Exactly. The parietal cells in your stomach actively secrete hydrochloric acid, dropping the localized pH dramatically to break down proteins and kill ingested bacteria.
But when that system overproduces acid, causing damage to the stomach lining, we utilize antacids.
Right.
A common one is magnesium hydroxide, also known as milk of magnesia. It acts as a mild base, gently neutralizing the excess hydrogen ions without pushing the stomach's pH too far in the opposite direction.
The mouth relies on a similar, carefully managed balance. The enamel protecting your teeth is made of calcium phosphate, specifically crystalline hydroxyapatite.
Hardest substance in the body.
It is, and it does not dissolve in water. However, when the pH in your mouth drops below 5.5, the environment becomes acidic enough to actively demineralize and corrode that enamel.
That drop in pH is caused by bacteria in the mouth metabolizing leftover sugars and producing acidic byproducts.
It is a slow chemical degradation of your teeth.
Which is why toothpaste is deliberately formulated with basic compounds.
Aye.
It's designed to immediately neutralize those bacterial acids and raise the pH of the mouth back above that 5.5 threshold, halting the demineralization process.
What's fascinating here is how often this acid-base dynamic is utilized in nature for defense, and how nature simultaneously provides the chemical countermeasure.
The honeybee sting is a classic example of natural chemical warfare.
Oh, yeah.
When a bee stings, it injects a complex venom that contains acidic compounds, primarily formic or methanoic acid.
Causing pain.
The introduction of this acid into your tissues causes immediate cellular damage and pain. However, because the primary irritant is an acid, applying a mild base like a baking soda paste to the sting site facilitates a neutralization reaction right at the skin level, mitigating the damage.
Plant biology employs this tactic as well. The stinging nettle is a wild plant covered in specialized hollow hairs called trichomes.
Basically, little needles.
When you brush against them, the fragile tips break off, transforming the hairs into microscopic hypodermic needles that inject methanoic acid directly into your skin, causing a severe burning rash.
But the surrounding ecosystem offers a direct chemical remedy.
The dock plant.
Yes. The dock plant, which often grows in the exact same soil and environment right next to the stinging nettle, produces basic compounds in its sap.
So convenient.
The traditional remedy of crushing a dock leaf and rubbing it over a nettle sting works because the basic sap physically neutralizes the methanoic acid injected by the nettle.
The chemical weapon and the neutralizing agent evolve side by side.
It is a brilliant display of chemical equilibrium in the wild. And this constant exchange acids donating protons, bases accepting them, inevitably leads us to the final category we need to examine.
Well, salts.
Salts. While the general public uses the word salt exclusively for sodium chloride on the dinner table in chemistry, a salt is any ionic assembly of cations and anions that form as the byproduct of an acid-base neutralization.
Though sodium chloride is undeniably the most prominent salt, whether evaporated from seawater or mined from halite deposits as rock salt, it is a foundational pillar of human civilization.
It really is.
Its importance was so profound that Mahatma Gandhi utilized the British monopoly on salt as the catalyst for the Dandi March, turning a simple chemical compound into a powerful symbol of the Indian independence movement.
Beyond its historical significance, sodium chloride is the raw material for a massive sector of modern industrial chemistry, primarily through the chloralkali process.
Right. What is that exactly?
In this process, a concentrated solution of sodium chloride in water, known as brine, is subjected to electrolysis.
So when a strong electric current is passed through the brine, the molecules are systematically torn apart at the electrodes.
Correct.
At the anode, chloride ions lose electrons and pair up to form chlorine gas. At the cathode, water molecules are split, releasing hydrogen gas and leaving behind hydroxide ions in the solution.
And those hydroxide ions pair with the sodium ions, leaving us with a solution of sodium hydroxide.
The chloralkali process is an industrial powerhouse because every single one of those three byproducts, chlorine gas, hydrogen gas, and sodium hydroxide, is vital for global manufacturing.
The chlorine gas produced is routed to react with dry slaked lime to synthesize bleaching powder.
Which is essential.
Bleaching powder is essential for purifying municipal drinking water supplies and for bleaching wood pulp in the paper industry.
And the chemical derivatives keep spinning off.
Yeah.
We previously discussed baking soda, or sodium bicarbonate.
Yeah, the heartburn cure.
It is manufactured on an industrial scale and is fundamental to the baking industry. When baking soda is heated in an oven, it thermally decomposes, releasing carbon dioxide gas.
Those expanding bubbles of carbon dioxide get trapped in the dough, which is exactly what forces breads and cakes to rise and achieve a soft, spongy texture.
That exact same rapid release of carbon dioxide is utilized in soda acid fire extinguishers too, where the sudden generation of heavy CO2 gas smothers a fire by displacing the oxygen it needs to burn.
Furthermore, if you take that sodium bicarbonate and heat it to force off water and carbon dioxide, you produce sodium carbonate.
Right.
When you recrystallize sodium carbonate from water, you get washing soda.
Ah, washing soda.
Washing soda is critical in glass manufacturing and is the specific chemical agent used to bind with calcium and magnesium ions in hard water, effectively removing permanent water hardness and allowing detergents to function properly.
But when we talk about salts interacting with water, there is a structural phenomenon that often defies common sense.
Oh, this is a great part of the text.
Our sources detail the concept of the water of crystallization, which is the illusion of completely dry crystals. If you examine copper sulfate crystals, they are a vibrant, deep blue color and feel entirely dry.
But their internal molecular geometry tells a different story. If you place those seemingly dry blue crystals into a test tube and apply direct heat, the crystals undergo a visible transformation.
What happens?
Tiny droplets of liquid water condense on the upper, cooler walls of the glass tube, and the copper sulfate itself loses its blue color, turning into a stark white powder.
The heat breaks the structural bonds holding the water. The white powder is anhydrous copper sulfate. But if you let that powder cool and add just a few drops of liquid water back onto it, the water integrates back into the molecular structure, and the vibrant blue color instantly returns.
This is because those water molecules were never just making the salt wet. The water of crystallization refers to a fixed number of water molecules that are chemically bonded within the crystal lattice of the salt.
They are integral to its shape and color.
Exactly. For copper sulfate, exactly 5 water molecules coordinate with each copper ion to form that blue crystalline structure.
This principle of locked-in water applies to other crucial materials as well. Gypsum is a naturally occurring sulfate mineral that fundamentally contains 2 molecules of water of crystallization within its lattice.
And harnessing the precise thermal manipulation of those water molecules is how we manufacture a vital medical material.
Plaster of Paris.
Right. If you heat raw gypsum in a kiln to exactly 373 Kelvin, the thermal energy forces the lattice to expel exactly 1.5 of those water molecules per unit.
The resulting material is calcium sulfate hemihydrate. Because it was historically mined in abundance near the French capital, we know it universally as plaster of Paris.
Plaster of Paris is a fine white powder. When medical professionals mix it with a specific ratio of water, the hydration process reverses.
It drinks the water back up.
The calcium sulfate hemihydrate rapidly reabsorbs the water molecules, reverting chemically back into solid gypsum. As the crystal lattice reforms, it expands slightly and hardens into a rigid, impenetrable mass, which is why it is the perfect material for setting and immobilizing fractured bones while they heal.
It is remarkable to trace these connections. We started this deep dive exploring how a simple base like baking soda accepts protons to cure heartburn.
And look where we ended up.
We've navigated through the violent electron transfers of zinc and acid, the crucial need for water to activate hydrogen ions, the precise, narrow pH window that dictates our survival, and the hidden structural water inside crystal lattices that allows us to mend broken bones. The mechanics of acids, bases, and salts are the mechanics of life itself.
They govern the parameters of existence. And looking at the strict limitations of our own biochemistry, this raises an important question.
Okay, I'm listening.
A scientific thought experiment based on these parameters. We have established that human biology, and indeed the vast majority of life on Earth, is absolutely dependent on maintaining a highly specific narrow pH range right around 7.0.
Right.
We are fundamentally calibrated to a neutral, aqueous environment. to the point where an environment like the sulfuric acid atmosphere of Venus is instantly lethal.
Right, our proteins would denature immediately.
But as astrobiologists search the cosmos, it makes you wonder, is our neutral pH requirement a universal rule for life, or just a localized adaptation?
Oh, wow.
Could there be entire biospheres built on alternative biochemistry? Alien organisms that have evolved to thrive in environments with an ambient pH of 1, utilizing concentrated acid as their primary solvent.
Or life forms structured around extreme alkalinity.
Exactly. If we ever encounter such extremophile life, the very environment that sustains them would instantly dissolve us. We might represent just one incredibly narrow sliver of biological possibility on a much wider, more volatile chemical scale.
That is a phenomenal, albeit slightly intimidating thought to leave on. The idea of alien life forms operating on an acid-based reality, completely foreign to our own.
It's wild to think about.
It is definitely something for you to ponder the next time you are baking a cake or using a fire extinguisher, watching the carbon dioxide gas expand. Thank you so much for joining us on this